All right, what I want to do next, although we will be talking more about relativity as we go, is to start investigating the particle properties of electromagnetic waves. And this will, in some places, find a symmetric counterpart with the wave properties of particles. So it turns out that electromagnetic waves have particle-like properties, but particles have the properties of waves too. And so it works both ways. But to understand this better, let's just look a little bit at a historical perspective. And what I wanted to do first is look at the history of our understanding of atoms. Because there's an analogy between atoms and the particle properties of waves. With atoms, we have a long history of trying to understand what makes up matter. And so the Greeks, back in the time of Democritus, many centuries BC, concluded that there must be an indivisible unit, or quanta, if you want to think of it that way, of the any particle of matter. So if you could break down this table, in other words, I could take this table and I could cut it in half. I could take that half and cut it in half again, take that half and cut it in half again. I could keep taking different pieces of this table, continuing to cut the half in half. And so they wondered, way back thousands of years ago, whether this process of subdivision could go on indefinitely, or whether you would get to a certain point where there was an indivisible unit of matter. And somehow they intuitively deduced that there was an indivisible unit of matter that they called the atom. Okay, and so that atom then, if you could build up from that, you could then make configurations of atoms which could take on the material properties of any solid subject, object. And so with the atom then, we had, this was the indivisible unit of matter. Okay, and so this, believe it or not, back in the 1900s was still not fully understood or accepted, but the Greeks had it down thousands of years ago. And so with electromagnetic waves, there was a similar kind of a consideration. If you took an electromagnetic wave, like a light wave, and you cut that wave in half, then you cut that half in half again, then you cut that half in half again, and you continued this process of subdivision, could you continue to cut it in half forever? Or would you eventually get to an indivisible unit of the electromagnetic wave? And so it's believed that you could continue to break it in half forever. And it was thought at first that it was a continuous property. So if the electromagnetic wave is continuous, then this process of subdivision could happen to infinitesimally small distances. But if this in fact is the case, you could continue to cut the light wave in half, down and down and down, farther and farther and farther. There were mathematical consequences to this. And so the conclusion then that this was true led to a conflict with observation. And so the conflict came with the ultraviolet catastrophe. And so this involves then the intensity of light output from the sun. As a function of the wavelength of the light. Now for light here, I actually mean any form of electromagnetic radiation. So I'm not just talking about light. And so if we look up at the data projector, what we see is the theory based on our classical data. And so this is the ultraviolet catastrophe, because you see then that the intensity of light approaches infinity as we get to shorter and shorter wavelengths. And so we're talking then about having way too much energy or intensity of the wave at the ultraviolet wavelength. And then if it was the ultraviolet catastrophe, it would be the X-ray nightmare, because at even shorter wavelengths, the X-rays would be even more intense than the ultraviolet radiation was. And so we see then that this is the contradiction with experiment that we find by assuming that electromagnetic waves are continuous. But Planck's theory gives us the right answer. This is our standard black body radiation curve. We notice that with Planck theory, we have the wavelength peaks out at a certain point. Like with the sun, this is kind of in the greenish yellow part of the electromagnetic spectrum. And a lot of the green light is filtered out by the atmosphere, so the sun looks fairly yellow to us. But it would look a little greener if we were up above the surface of the atmosphere. So that would be the peak. Then as we get to lower wavelengths, which would be higher frequency, like X-ray, the intensity would drop. And it would also drop at longer wavelengths, like radio. So this is exactly what's observed. And this was the answer that was gotten from Planck's theory. So let's just take a look at what that involves then. Using Planck's theory, Max Planck assumed that you can break up electromagnetic waves into an indivisible size. Chunks or pieces called photons, where the energy of the electromagnetic wave is an integer multiple of the energy of a single photon. And the energy of a single photon, according to Planck, would be equal to Planck's constant. Of course, he gets a constant named after him because it was his theory. He deserves it. It's a small number multiplied by the frequency. So this is the frequency of the electromagnetic wave. So in other words, you could keep breaking this electromagnetic wave up into smaller and smaller chunks, but eventually you get down to just 1 times Planck's constant times the frequency. And so when we apply this rule to the intensity of light coming from the sun, we get the right answer. For the intensity of sunlight. Which is the black body radiation curve. And so here's intensity versus wavelength. So we get this kind of a plot then for the intensity of an electromagnetic wave versus its wavelength for the light that comes in from the sun. So this is the right answer. But the idea that you have a bunch of these little bullets, basically, these little photons that make up an electromagnetic wave, it doesn't seem consistent with the idea of a smooth continuous wave. And one person said, this is a lot like saying that you have a water wave breaking on the shore and that a little piece of that water wave could hit a shell and knock it 2 miles away. You know, because basically we're saying that this wave is made out of little bullets that are all moving at the speed of light that we're calling photons. And so that doesn't seem very consistent with the whole idea of a continuous wave. But it is interesting to note that Isaac Newton took issue with almost all of his contemporaries 250 years ago by saying that he believed that light was a particle and not a wave. And then he was disproven, and the whole idea was kind of, they ridiculed that idea. But now it looks like Newton was partly right, although his reasoning was not correct for why he thought it was a particle-like properties. He still had it, he had an element of it right that people didn't realize was true until the early part of the 20th century, back around the year, this is around year 1900 or so, that Planck came up with this. And so let's see then if we could actually calculate the energy of a photon using Planck's equation. If the frequency is equal to 5 times 10 to the 14 hertz. Okay, so this would actually be a visible frequency of light. And so the energy then associated with that would be Planck's constant times the frequency. And if you had a whole bunch of these photons that made up a smooth continuous, what looked like a smooth continuous electromagnetic wave, then the total energy of that would just be some integer multiple of Planck's constant times the frequency. The analogy with that is we could take a certain number of atoms, and we could, in a table, we could say that the total number of atoms is just an integer multiple of how many atoms there are. And so similarly here, we could say the total energy is an integer multiple of the energy of one photon. Now Planck's constant, 6.63 times 10 to the minus 34, that has units of joule seconds, be multiplied by 5 times 10 to the 14 hertz. Now hertz has units of 1 over second. It's actually cycle per second. But cycle isn't technically a unit, just like an angle isn't technically a unit. So this is like 1 over seconds times seconds. That gives us energy of joules. Okay, so that looks okay. So if we multiply this out, we get a pretty small number. We get 3.31 times 10 to the minus 19 joules. But if you recall, before we were saying that for really small numbers like this, on the order of an electron volt, which is 1.6 times 10 to the minus 19 joules, this looks like it would just be a couple of electron volts. So let's go ahead and change that to electron volt units. So that would be 1 eV for every 1.6 times 10 to the minus 19 joules. And that would give us 2.07 eV. So what this is telling us then is that visible light has a photon energy that's on the order of, looks like, a couple of electron volts. Okay? And so that would be a much more natural unit of measurement for the energy of an electromagnetic wave. Now, using the fact that frequency times wavelength equals velocity, and in this case, for a photon, the velocity is the speed of light, we can see that energy is Planck's constant times the frequency is also hc over lambda. So oftentimes we'll be using it in this form, and we'll be expressing the energy as a function of the wavelength of the radiation rather than as a function of its frequency. And so that being the case then, we could solve for the wavelength, lambda, and we could just use this equation if we want, and that would be hc over E, which would be 6.63 times 10 to the minus 34 joule seconds, times C, 3 times 10 to the 8 meters per second, divided by the energy. We'll want that in joules. So that's 3.31 times 10 to the minus 19 joules. And that gives us 6 times 10 to the negative 7 meters, or 600 angstroms. Now, 400 to 700 angstroms is visible light, so 600 angstroms would probably, I would say, be, this is the longest wavelength, so this might be like yellow maybe, orange or yellow, because 700 angstroms is red and 400 angstroms is violet. Okay, so 600 angstroms, but it's visible light. And so that would be the wavelength, and that is how we could get it directly from our energy relationship using Planck's equation. Another way of getting it, of course, is to just know what the frequency was here, and then we could set that frequency equal to the speed of light, or I'm sorry, the wavelength equal to the speed of light divided by the frequency. Okay, so this looked promising because it gave us the right answer for the black body radiation. But because of all of the difficulties involved in conceptualizing a particle that has wave-like properties, this wasn't really enough to completely convince everyone that the electromagnetic wave is made out of low photons. And so more evidence was needed. So the next piece of evidence that came along was the photoelectric effect. Now, in the photoelectric effect, here's our puzzle that needs to be solved. Turns out it was Einstein that solved this puzzle, and Einstein eventually ended up getting the Nobel Prize in physics for the photoelectric effect, even though historically he's remembered as being the founder of relativity, and he hated quantum mechanics. And yet, so ironically, he gets his Nobel Prize for quantum theory and not for relativity. But relativity, it turns out, was too controversial at the time. And we'll talk more about general relativity soon. But I want to get into the quantum aspects of reality before I talk about general relativity. All right, so here's the puzzle. We got a piece of metal, and that piece of metal has a work function phi. And that is the minimum amount of energy that's required to evaporate an electron from the metal. And of course, a metal is a conductor of electrons. But if you can get one of those electrons to a high enough energy, you might be able to just kick it right off the surface. So the idea here is kind of similar to what would happen if I took this pin and I threw it fast enough up through the atmosphere. I'd have to give it enough energy so that it would achieve escape velocity. So essentially, that's analogous to what we're talking about here, is we're trying to get the electron to escape from the metal, and our mechanism is going to be incoming photons. And so what was observed here is that if you had the energy too low, that means too low of a frequency. According to Planck's law, then no electrons escape. Regardless of the intensity of the beam. Okay, so that is the kind of the stumbling block in understanding this. Because if you say have red light, that's going to have a low energy in terms of visible light. If you shine a little bit of red light down onto here, you are going to you're going to have a certain amount of energy. You can double that energy by putting more red light in there. And you could triple the energy by putting even more red light in there. You could eventually get enough intensity of the light beam so that the metal would melt. And yet no electrons would be evaporated off, regardless of the fact that you kept pumping more and more energy into the system. You would think that you're giving the electron enough energy to escape, but it wasn't escaping. And the metal would melt before a single electron would escape. On the other hand, it was found that if you increase the frequency to a certain critical point, electrons would start escaping. At a critical frequency, Fc, we have a critical wavelength, which would be C over F critical. electrons escape with negligible velocity. Which means that there's very little kinetic energy left over. Okay? But electrons will escape when we reach a certain frequency for the electromagnetic waves. And above that frequency, electrons escape with the maximum kinetic energy. Regardless of the intensity of the beam. So in other words, let's say that blue light is higher than the critical frequency. Then we add a little bit of blue light, and we get a couple of electrons with a maximum velocity that can escape. If we add higher intensity, then we get more electrons escaping, but with the same maximum velocity. So in other words, the velocity of an individual electron never exceeded this value, despite the fact that you had an increasing intensity, which you would think would kick electrons up to higher velocities. So over here, we're seeing that you can melt the metal and no electrons escape. And here we're seeing that as we increase the intensity of the beam, we get more electrons escaping, but with the same maximum velocity. And so all of this information is gathered together, and it was creating this big, huge, confused group of scientists that didn't really know what to do with it. And so they went to Einstein, and they asked him what he thought of it. And so he's walking with a scientist around on a beach somewhere, and Einstein stopped for a second after hearing what the problem was. And he goes, "Oh, I know why that is." And he scratched out this equation in the sand. And that was it. He gets his Nobel Prize for that. And he's considered to be one of the founding fathers of quantum theory. And so what was Einstein's solution? Well, Einstein's solution is that the light is broken up into photons. Where the energy is equal to hc over lambda, which is the Planck relationship. And the electrons only absorb one photon at a time. So if the electrons can absorb two photons, the probability of that, Einstein deduced, would be low. Then what you really need to do is just look at a single electron and the interaction between a single electron and a single photon. Then you can multiply that by however many photons are interacting with how many electrons to get the total property of the system. But for each electron, you're going to have the energy of the photon. This was Einstein's equation, equals the work function for the metal plus the kinetic energy that's left over. And since this is happening one photon at a time, only one photon is going to interact with one electron. And so some of that energy of the photon is used up with the work function. And at the critical value, there's no kinetic energy left over. So that satisfies that relationship. We can get electrons escaping, but with zero kinetic energy at the critical energy for the photon. But at values that are greater than that, we're only going to get one value for the kinetic energy. That's the maximum kinetic energy, kmax. Now, could the kinetic energy be less than this? The answer is yes, but only because of interactions of the electron with the environment. And so if the electron doesn't interact appreciably with the environment, then the energy of the electron would be the kinetic energy maximum. But you're going to get a whole spectrum of other values for the kinetic energy that are just dependent on how often the electron gives up energy to the, say, the air molecules on its way out. So this was Einstein's equation. So let's use it to see if we can get the right answer. Let's say that for a particular metal, we have a work function of, let's say, 2.5 electron volts. So this is the minimum energy required to evaporate an electron. From the metal. And so let's first find the critical wavelength of the photon. In other words, at what wavelength will the electrons escape, but with no extra kinetic energy left over? Okay, and so what we can see here then is that the energy of the photon would be hc over lambda critical is equal to phi plus 0, because there's no kinetic energy left over. So the electron has been evaporated, but with nothing left over to move the electron at any appreciable speed. So we can then find that critical value for the wavelength. Once we found that, then we know that any wavelength lower than that is going to get the electron to escape with some non-zero value for the kinetic energy. But if the wavelength is greater than that, the energy is inversely proportional to the wavelength, so higher wavelength means lower energy, then no electrons would escape. Okay, so first we're finding that critical wavelength, and so lambda c is going to be phi divided by hc. Now phi is given to us in electron volts, but we're going to need to convert that into joules before we can figure out what the wavelength is. Okay, so this is 2.5 eV times 1.6 times 10 to the minus 19 joules per eV divided by 6.63 times 10 to the minus 34 joule seconds times C, 3 times 10 to the 8 meters per second. right, so that's going to be let's try that one more time. So that's going to be 2.01 times 10 to the 6. Oh, wait a minute. HC over lambda. Wait a minute. So lambda is HC over phi. Sorry. That was the problem. All right, so this is 6.63 times 10 to the minus 34 times 3 times 10 to the 8 meters per second divided by phi, which is which is 2.5 times 1.6 times 10 to the minus 19. So it's reciprocal of what I had there. So I did the wrong answer. So I just hit the 1 over button. And so that gives us 4.97 times 10 to the minus 7. And that would be meters, or that would be 497 nanometers times 10 to the minus 7, that's 497 nanometers. So that would be in maybe the green or blue part of the electromagnetic spectrum. Okay, so that's our critical wavelength. So let's go to a little lower wavelength and let's find kmax. If the wavelength is less than the critical wavelength, so in other words a higher energy, let's set it equal to the minimum wavelength of visible light that we can see, which would be essentially violet light. Okay? And so if we want to do that, then we can look at the photoelectric effect equation, Einstein's photoelectric equation, and we can say that kmax equals the energy, which is hc over lambda, and then that's going to be minus phi. So the difference between the energy of the photon and how much energy was required to evaporate from the metal is going to be how much kinetic energy is left over. Okay, and so here then we've got h, 6.63 times 10 to the minus 34 joule seconds, times c, 3 times 10 to the 8 meters per second, divided by lambda, which is 4 times 10 to the minus 7 meters, minus, and then here we've got phi, which is 2.5 eV times 1.6 times 10 to the minus 19 joules per eV. Just the difference between the total photon energy and the energy required for it to escape from the metal. Okay, so that's going to be 4.97 times 10 to the minus 19 joules minus 2.5 times 1.6 which is 4 times 10 to the minus 19 joules. So kmax would be equal to 0.97 times 10 to the minus 19 joules, or 9.7 times 10 to the minus 18 joules. If we wanted to convert that back into electron volts, which we don't have to do because we're done here, we could just say 1 eV for every 1.6 times 10 to the minus 19 joules. So it'd be a little less than an electron volt. Oh, that's 9.7 times 10 to the minus 20. Whoops. There we go. Okay. So that gives us 0.6 electron volts. All right, so that would be the maximum kinetic energy of that electron under those conditions. Now we might wonder, well, is that kinetic energy of the electrons relativistic or non-relativistic? Well, to find out, let's take a look at the rest energy of an electron. Okay, so the rest energy of an electron would be the mass of the electron times the speed of light squared. So that would be 9.1 times 10 to the minus 31 kilograms times 9 times 10 to the 16 meters squared per second squared. So that would be 0.51 times 10 to the, let's just work the whole thing out. So that gives us 8.19 times 10 to the minus 14 joules. And we could, now this is a much larger amount of energy than electron volts. And so we could define 1,000,000 electron volts as 10 to the 6 eV. And so that would be equal to 10 to the 6 times 1.6 times 10 to the minus 19 joules, or 1.6 times 10 to the minus 13 joules. So let's do that here. Let's convert this into 1,000,000 electron volts. 1 MeV divided by 1.6 times 10 to the minus 13 joules. So what we get here then is 0.51 MeV, million electron volts. Okay. And so here we see that the kinetic energy is 0.6 electron volts. So the total energy is equal to the rest energy, m naught c squared, plus the kinetic energy. And so the kinetic energy clearly is way less than the rest energy. If K is much, much less than m naught c squared, then it's non-relativistic. So in other words, if we can compare the kinetic energy of the electron to its rest energy, and we find that that kinetic energy is way, way less than the rest energy, we can conclude that the electron is just moving at speeds that are way less than 1/10 the speed of light. If that's the case, then we could easily figure out the velocity of the electron by setting kmax equal to 1/2 mv squared, and then just solving that for the velocity. Okay, so this is non-relativistic, because the kinetic energy is way less than the rest energy. Now what if we were talking about a proton? With a proton, that'd be mass of the proton times the speed of light squared. That would be 1.67 times 10 to the minus 27 kilograms times 9 times 10 to the 16 meters squared per second squared. This gives us a much bigger number. Uh, 1.5 times 10 to the minus 10 joules. If we convert that to MeV, 1 MeV for every 1.6 times 10 to the minus 13 joules, we would get, for the proton's rest energy, this is 931.5 MeV, where M is 1,000,000 electron volts. Okay, so the proton's rest energy is something like 2,000 times greater than the rest energy of the electron. And so if we had a kinetic energy in a problem that was way, way less than this rest energy, say it was 10 electron volts even, that would be nothing compared to 931.5 MeV. We could conclude that that proton was non-relativistic as well. However, if the rest energy is comparable to the kinetic energy, then we already knew from our previous calculation that that would give us something like an 86% velocity for the speed of light, and that would be relativistic. Okay, so a lot of times what we'll do to see whether something's non-relativistic or relativistic in any given problem is to just compare the kinetic energy to the rest energy. And then we could easily figure out the velocity if it, say it's 1/2 mv squared, and it's a non-relativistic problem. Okay, so that then is essentially then how we calculate the maximum kinetic energy for an electron, and then by comparing the energy to the rest energy, we can then conclude in this particular kind of a process we're dealing with something that's non-relativistic. This is a way in which photons can interact with matter. This is not just confined to metals. You have interactions between photons and electrons in any material that can cause the electron to be knocked free from an atom. Okay? And by absorbing, it's a photoelectric effect type of a problem. By the electron absorbing the photon, it gives the electron more energy, and then that electron can escape from the atom. And so if we're dealing with visible light, that typically will interact with matter by means of the photoelectric effect. But there are other kinds of interactions of photons with matter that are relativistic, and in some of these situations you can actually produce matter out of energy. Okay, so you can take photons that have a high enough energy, and you have enough energy left over between the photon interactions to produce matter. Okay, and so in those kinds of situations, the energies associated with the problem can be relativistic.